So welcome everyone to my presentation on the evolution of functional programming in C++. A little bit about me. My name is Abel Sen. I'm a functional systems programmer primarily focused on languages like Haskell, C, and C++. You can find me basically on all the things. Feel free to reach out to me at any time, especially after the talk or the conference, to reach out with any doubts you may have. I'd love to talk with you all further. So here's the agenda. I'm probably going to abbreviate this a bit since we've had previous issues, but roughly, we're going to try to understand the origins of C++ and its ethos as a language. And then we're going to dive into the meat of the presentation, which is going to be about understanding the evolution of functional programming, or FP, in C++ from ISO C++ 98 through ISO C++ 23. In particular, we're going to focus on understanding how each FP feature benefits us as programmers, and we're going to better understand why they're so important by comparing these features to the features that are offered by Haskell as a purely functional programming language, and how adopting these features can make our C++ more expressive. We're going to then talk about how FP is going to look like in C++ 26 and beyond, and then finally engage in some musings about performance. So what is C++? So you may not know this, but C++ was actually inspired by another language called Simula, which had very powerful type checking and abstractions like coroutines. It was actually used by Dr. Bjarne Stroustrup in his work for his PhD thesis for implementing a simulator for distributed systems. It was very nice to use, but however, it was too inefficient for him to run on a shared mainframe-like machine that he had to share with other university students at the time, and then that caused him to have to rewrite the entire project into BCPL, which is a very low-level language, and that sort of started the gears rolling. So when it came time for Dr. Stroustrup to work at Bell Labs in Murray Hill, New Jersey in the States, he eventually found himself once again working on a distributed systems problem. And it was at that point that he realized that he couldn't repeat the Herculean effort of writing such a system in a language like BCPL. And that was really the impetus for the creation of what was then known as C with classes and what we now love and enjoy as C++. So I believe I'm going to skip over this slide, but basically this gives you some idea of the core ethos and principles of C++. So for the sake of time, we're going to move on. So I'm going to start by talking about C++ 98, the first ISO standard release of the language. So the core functional features of this release boil down to functions as first-class citizens and generic programming, which you can further expand into function pointers, references, pointers to members, function objects, and templates. So we'll start with the first one. So when we talk about functions as first-class citizens, it means nothing more than the ability to pass functions to functions, return functions from functions, and essentially bind functions to names. So when we get over to function pointers, it's really a holdover feature from the language C, off which C++ is based. And I'd say this feature alone already makes this concept of functions as first-class citizens a primary feature in the language. So the key benefit of something like function pointers is that you get the ability to refactor high-level algorithms out of concrete implementations. So let's discuss a real-world motivating example. And of course, we know that there's no more real-world example than that of sorting lists, because I know that's what you do as professional programmers all the time. So pretend you need to do it two ways, right? Your boss comes up to you and says, we need to A/B test two variations of quicksort, one using Lomuto partitioning, another using Hoare partitioning. Yeah, we're going to make it intentionally onerous to see how FP is going to benefit us. We'd prefer for it to be maintainable. And so you, as the humble programmer, are left wondering, what exactly do we do? So here's our initial stab at the problem. So we're going to start off with a std vector of ints, push a bunch of numbers onto it, and then copy those elements into another std vector to a A/B test or other algorithm. And then finally, we have the two invocations of the two quicksort algorithms, one using Lomuto quicksort and the other using Hoare quicksort. And so for Hoare quicksort, we obviously have a driver function, which calls into an impl. The impl takes not only the std vector, but also the low and high indices. And then finally, the Hoare partition algorithm is lighted for simplicity, but it does its thing. And then likewise, we have the Lomuto quicksort driver function, followed by its impl, and the Lomuto partition algorithm itself, which we have once again lighted. So overall, what we see here is essentially the same driver skeleton, the same algorithm skeleton in which we partition to get the midpoint and then recurse into the left and right sides. And the only different thing occurring here is the partition strategy. So an idea we can pursue is to extract out that strategy, this function, out as a parameter. And so that's what we're doing here. Instead of having two different types of quicksort functions, we have a single one which accepts an additional argument of type pointer to function, which is our partitioning strategy. So in the first case, we pass an address to Lomuto partition, and the second, we pass an address to Hoare partition. So now we have a single quicksort function which has this additional parameter of type pointer to function. And in the impl, likewise, we accept another parameter. We drill that down so that it also accepts a pointer to function representing our partition strategy. And then the partition strategies themselves can remain exactly the same. So what are the benefits of what we've done here? So the sorting algorithm is now separated out from the concrete partitioning strategy that we use in each case. And the benefit additionally is that we can now refactor or extend this code with additional strategies in the future without adding unnecessary code bloat. The cons, of course, are that we have this additional parameter drilling of this function pointer, and that we may invoke the cost or the penalty of the runtime function pointer dereference. So now we move on to function references. This is basically the same in all honesty. It's similar to function pointers, but just like regular references we all know and love, they cannot be reseeded, and they can never be null. So let's revisit the previous example to refactor. So there's really not much going on differently, except we got rid of the address of operator, and now we're passing the names to these functions, so they're taking function references. And so as you might expect, instead of pointer to function, these functions take reference to a function, so we update the driver and likewise the impl. So I'm going to skip ahead a bit and move to function objects. And to motivate function objects, we're going to talk about the functional header. The functional header is a part of the CPlusPlus standard library that defines a set of what I'll call algorithm templates that compose well, or rather a set of function objects that compose well with what I'll call algorithm templates. So a function object is really nothing more than a class or a struct that implements a call or a parentheses operator. And the benefit of something like function objects in the world of CPlusPlus is that they introduce closures and partial application to the world of C++. So let's do another refactor. And for the sake of time, I'm actually going to skip this. So if you're already familiar with templates, I'm basically going to templatize this function, so I'm going to be able to use any type of partitioning callable-like thing in my quicksort algorithm. So I'm going to skip through that for the sake of time. So basically the idea is to keep visually the client code the same, but templatize the quicksort implementation so we can use any type of callable thing. So the benefit of doing that is that we can actually pass function objects to quicksort to specify the partition strategy. So here I'm defining a low muta partition struct with a call operator defined. It takes a vector, the low and high indices, and then does the partitioning and returns a midpoint. Likewise with the whore partition algorithm. And then now in the quicksort invocations, instead of passing a function reference or pointer, we can pass instances of the low muta partition and whore partition structs respectively. So the benefit of this particular refactor, we get potentially better inlining due to the use of these template instantiations and the use of these stateless objects. The con, however, being the additional template instantiations and the binary bloat that they may cause. Now, that was a bit of a contrived example, to be honest. So the real power of function objects in CPlusPlus is that they give us the ability to emulate closures by capturing values or variables upon construction. So here we're seeing an example of a struct called add number, or class called add number with a private variable number, has a standard constructor, and it's a call operator which accepts another int. And upon receiving that int, it will add that value to the privately stored member variable number to retrieve or return the summation. So how might that be useful? So if we have some std vector of ints, some collection of data, and we'd like to transform that data by adding some user-supplied values, say x here, it's just hard-coded but standing in for some dynamically generated value, and we'd like to add that value to each element of our starting collection and generate a new one, we can do that as follows by calling into the STL algorithm of std transform and passing to it as our unary transformation function an instance of add number of x. So add number of x, by taking x as part of its constructor upon initialization, is in a sense closing over the x from the enclosing lexical scope and forming a unary function object which will give the result of adding x to a supplied value. So in this particular code example, there's a problem because there's already a function object in the STL that expresses this desired computation, but its signature is a bit too general. So we want to avoid reinventing the wheel. So I'm talking about nothing other than std+, which can be specialized to any number of types. So in this case, I'm reducing a collection of integers into a single summary value by using std+ specialized to int. And basically, it's a binary operation that adds two elements together. And so we get our summary value that way. And so the solution to our original problem is to specialize std+ with a parameter we already had on hand. So in this case, we're once again calling into std transform, but now we're passing as our transformation function the result of std_bind first. So std_bind first in this case takes as its first argument an instance of std plus int specialized to std plus specialized to int, and then as a second argument we're passing in that value of x. So x essentially gets bound to that first parameter of this binary function object to turn it into a unary function object, which then expects another value to add on to x. So similar to bind first, it's also bind second for binding the second parameter of a binary function object. And then if you find std plus and friends very interesting, you'll find things like minus and equal to for you to use in the functional header. So I'll skip over pointers members completely actually, because if you look into it, it's pretty much the same game if you understood what we've seen so far. But we'll go on to templates for now. So when we talk about generic programming with templates, templates allow you to specify generic recipes from which you can bake concrete classes or functions. So they enable you to specialize that recipe in the case of specific classes if you need additional space or time performance. So this time I promise is a more realistic example. Here is our humble stack, which is templatized on a type named T, and it comes with the usual implementation of a linked list. It has a head pointer, comes with a default constructor, another user-defined constructor, and then push from pop and deconstructor operations. So of course, a user can do the standard things of pushing 1, 2, 3, getting 3, 2, 1 back out as they pop. But the interesting thing happens when we can specialize this template. In this case, I'm specializing the stack template in the case of Boolean, because we know in the case of Boolean, there's only two values, true or false. So we can get additional space performance by compressing the values in the stack into a bit set, essentially. And that's what we're doing here with this unsigned car star bit set. We refactor our internal implementation to make use of new utility methods like resize and some indexing functions. But the benefit is that as long as we're disciplined as library authors, we can expose exactly the same interface to our client. So once again, I'm still implementing a default constructor, another similar user-defined constructor, and push from pop and the destructor. And so now the benefit is the client, once they choose to instantiate a stack to the type name bool, they'll get exactly the same behavior on the surface, but they'll get additional space performance for free because we've done that additional work as a library author. So there's a lot of features we covered. So how might that compare with what we see already in a purely functional language like Haskell? The key thing to note about Haskell is that first-class functions are really the name of the game. And there's no OOP-style objects or classes to speak of. And the currency of programs are really defined by what we will call sum and product types. So let's see this in code. Haskell is a bit of a strange syntax for assigning types to values and functions. So here we're seeing add delimited by a double colon. And it says it takes a float and returns another function which awaits a float itself, and then finally returns the float result. So it's a function going from float to float to float to give you a summation, and likewise for mult. In this case, list sum is now taking a list of floats to compress it into a single float, the summation. So Haskell not only has simple functions, but also higher order functions which can take functions as arguments themselves. So in this case, we're defining list sum in terms of fold L prime. So fold L prime takes as its first argument a binary reduction operation, which in this case we're passing add, and then takes the starting value 0 and then the collection to reduce, which is x's. And we're doing a similar thing for list prod. And the other funny thing we can do is actually return functions from functions. So here we're saying that use list sum, depending on the value of the bool passed in, will either return list sum or list prod as its result. And then our main function, when we have a list of numbers 1 through 4, based on the value of true or false we pass into use list sum, we will retrieve either 10 or 24 as the output result. And lambdas and closures in Haskell, how does that work? So here we're doing a standard operation of mapping the addition of some value x over a collection of elements 1 through 5. And we see here that in this notation of in parentheses plus x, it's basically a lambda. In Haskell, there's no ceremony for lambdas. They're just regular functions in Haskell, except they're not bound to names. And we see that x is furthermore closing over the enclosing scope to capture that value of x. And furthermore, we can actually note that this is an instance of partial application since we're binding x to the first parameter of the normally binary function of the plus operator. And then user-defined data types. So data types are once again somewhat of a strange thing if you're not used to the syntax. So here defining a simple data type is called status, which can be defined in one of two ways, using either the sleeping constructor or the coding constructor. I'm sure the status is familiar to all of you as programmers. And then we can define so-called polymorphic data types. These are like our template data types in CPlusPlus. So we can have an optional A, which can be either created by a non-constructor or a sum constructor, which takes in an A and then gives you back an optional A. And then we can combine this notion of having variants or sum types with product types, which aggregate values into a single coherent whole. So here, stack of A can be either created by a nil constructor or by the cons constructor, which takes an A and a stack of A to give you back a stack of A. So since this is Haskell, there's no things as methods or objects, so we're creating everything in terms of freestanding functions to operate on our stack. And then when we get to our main function, we see the ways in which we can instantiate these data types. So we can have sum of 3, which is typed to optional of int. We can have none, which is typed to optional of int. We can also have none, which is typed to optional of string. So you might be confused by that, but the interesting to note is that for every possible instantiation of that polymorphic data type, there is a separate none constructor. So that is why we have to have that type indentation to disambiguate. And then finally, if we have sum of the string hello world, we get optional string. So I mentioned the idea of specialization in C++. So you might be wondering, how would we achieve that in Haskell? The thing is, it's actually quite difficult to do, at least the way I did it. It requires using things like type families and data families in Haskell, and it's definitely not as ergonomic as it is in C++. So I'd definitely say it's a win for the language of C++ in this case. So what I'll say about that is that C++ facilitates creating ergonomic and transparently performant data structures for your clients to use. So I'm going to skip any potential discussion about template metaprogramming in C++98. I believe that's a whole can of worms, so I think that's best left for a whole other talk entirely. So basically, we got functions as first-class citizens and generic programming with templates right off the bat with the first ISO standard release. We saw that Haskell may be more succinct, but it does come with more painful specialization in the case of polymorphic data types. So now we'll talk about C++11. So there are a lot of features here. There are lambdas, stood functions, stood bind and partial application, auto-type deduction, and additional compile time metaprogramming. So the first one, lambdas. So lambdas really encode this idea of functions as first-class citizens. They can be passed around and bound to names, and they can form closures to close over the variables or values in the enclosing scope. So the anatomy of lambda is not too different from that of a function, except the difference is we have in square brackets a list of captures we can do to capture variables or values by reference or by copy. So I'll explore this idea with a string/file processing example. Imagine if you're a Unix Linux programmer, you are trying to analyze the files in your directory. You might want to filter down those files into a list of files that correspond to program names. So here I'm making the simplifying assumption that any program is something that doesn't end in .txt. So I start with a stood vector of strings representing our dynamically generated list of files. I'd like to output that into a filtered list of programs. And so to do that, I once again call into the STL to call copyf. And then I pass to it as my predicate, filtering predicate, a lambda, which takes in a stood string, and then returns a Boolean indicating whether or not it ends in .txt. We can go further and actually capture variables with closures. So here I've refactored the previous example into another function. So filter files takes in the stood vector of strings and outputs the filtered list. Now here, this is not necessarily best practice, but just to illustrate the dynamism possible, I'm asking the user at runtime what their choice of ignored file extension they'd like to have. And I'm storing it into a local variable called ignored file extension. And then once again, I'm calling it as a copyif, but this time in my lambda, I'm actually capturing the value of that variable by reference so that I can use it in the body of my lambda. And so once again, I'm comparing that extension to the string to make sure it doesn't end in it. And so in our main function, as long as the user enters .txt for the ignored file extension, the result will be exactly the same. So stood function. This is especially important as a feature when you realize that lambdas and C++ each essentially define a unique type. So if you go to something like cpp_insights.io, I believe, and you compile your source code down into the lower level Clang representation, you'll see that each lambda is essentially backed by a function object. And not only are there function objects, we already have things like function pointers, references, pointers, and members, all things that are callable in nature. And if we don't know what type of callable we're going to return to a user ahead of time, stood function gives us the ability to generalize any such specific type into a uniform interface describing the input and output. So here I'm discussing a example inspired by streaming services. So I have an EM class plan with standard plus and ultra variants. A subscriber is represented by a variable plan of type plan and a member variable active last month of type bool. So here, if let's say I'm a streaming service operator and I'd like to deliver the best possible service to my most valued customers, but I'd like to understand only at runtime who my most valuable customers are. So in this function, I'm returning a stood function that takes a subscriber and returns a bool indicating whether they're a target audience. So I asked the operator runtime what they'd like as a choice of discriminator, either based on membership last month or by their subscription plan. And then based on the value of that choice, I either return a lambda. Bear with me, everyone. Okay, we're back. So based on the value of that choice, we either return a lambda indicating whether they were on the ultra plan or a pointer to member indicating whether they were active last month. So the lambda's here and the pointer to member is there. And so if you want to start out with a list of original database of subscribers and turn them into a target audience of subscribers represented here by a std vector, we can call into std_copyIf and then pass as our predicate the result of getQoS filter. And so regardless of whether the lambda or the pointer to member is returned, std function will generalize that interface into essentially a simple mapping from subscriber to bool. So I will skip std bind and partial application, or I will skip this initial part. So basically, so imagine if you're a machine learning researcher, right? You have this common problem of training a model, a bunch of data, you get that trained model, and you've received a new set of test data and you'd like to transform that collection into a new set of labels given by a prediction function. So I'm defining the simplest of machine learning models, which is the perceptron, and then I default initialize it, I train it on my data, and then I get my new test data, and then how I transform that test data into a set of predictions is by calling std transform, and then specifying as my unary transform operator the result of std bind. So std bind takes in as its first argument in this case the pointer to the predict member function, and then I'm passing in the address of the model object. So this pointer of that function gets bound to the instance of our model, and then I'm specifying _1 from the std placeholders namespace to specify that that value will be dynamically supplied for each instance of each invocation of the result of std bind. Auto type deduction. So this basically makes our lives as programmers easier by allowing us the ability to not have to specify types everywhere. So here we have a double x equals 2.0, very simple. But in the next line, we can say auto const x squared is initialized with x times x, and C++ will deduce for us that x squared is of type double from the initializer. Type reference on Haskell is very similar. We can say x equals 2.0, and the name, the type of that name will be deduced for us, except with a caveat that there's Hindley-Milner type inference, which is sort of bidirectional nature and a bit more sophisticated, but that's what we get with functional languages. And then finally, compile time metaprogramming. So here in C++11, what I feel is the interesting thing about compile time metaprogramming is it offers us the ability to emulate prototypical concepts that we got more concretely in C++20. So it's really backed by a number of features in C++11, and in particular SFINE, or substitution failure is not an error, which you already have back in C++98. So I'm going to talk about a mathematical object called monoid to motivate this. So don't be afraid of a monoid if you never heard of it. It's basically a set of elements S that has a dot operator. I'll call it dot. And basically, no matter what parenthesization of variables you use in a set of variables being combined with the operator, you'll get the same result. And then it has an identity element. So that's all it is. So the interesting thing with Haskell is that we can take a very ad hoc interface like a monoid and specify concretely in terms of types using type classes and ad hoc polymorphism. So here I'm saying any type A is an instance of a monoid if it exports these types, essentially the identity element, the combining operator, and mconcat, which takes a possibly empty list of monoidal values and combines them into one thing. And then I actually specified that any instance of a monoid can be default specified in terms of these value and function definitions. And then furthermore, I say that a valid implementer can be defined either minimally in terms of MMT and mappend, or simply just in terms of mconcat. So here, I'm defining two polymorphic data types, sum and product, representing the monoids of multiplication and addition over the real numbers. And then here, I'm actually defining the monoid instances for these polymorphic data types. So you'll note that in the type class head, I'm saying num of A as a constraint to ensure that a product of A is only a monoid for any A for which A is actually numeric in nature. So we don't have a garbage idea of mathematically combining non-numeric things. And furthermore, if you look at product, we choose to implement it in terms of mempty and mappend, whereas in sum, we choose to implement it in terms of mconcat. Now, this is not strictly necessary, but it may be in the real world for different type classes if you need more performance for certain type class instances. And so then, when you get to our main function, we'd like to either monoidally combine a list of numbers 1 through 4, either using the sum or product monoid, even though the internal implementations of the type class instances are different, we'll get the correct result since Haskell already knows that we have said that there are two minimal implementations that make a valid monoid instance. So here is how we do it in C++. It's quite cumbersome and it relies a lot on Sphene. And I believe I'll try to go through this quickly as possible. But basically, we introduce these dummy parameters to use for the purpose of Sphene in our template types for monoid, product, and sum. And so right in the definition of product and sum, we use std enable of t and std is arithmetic to ensure that for any instantiation of t, we have indeed arithmetic types. And then similarly, as we saw in Haskell, we choose to implement product in terms of mempty and mappend. Whereas in the case of sum, we choose to simply implement in terms of mconcat. And so here comes the real funny business. So when we want to implement a type class method in terms of a freestanding function, we have to check which internal implementation is backing that monoid instance. So in this case, we define a version of mempty, which uses decal type to see if the monoid is implemented in terms of mempty and Sphene otherwise. And then in this case, we use decal type to check if the monoid is implemented in terms of mconcat and Sphene otherwise. So we do this dance of defining two variants for each type class method to get all the freestanding functions we need. So then, if we now need a more sophisticated function like fold map, which lifts a collection of elements into a monoid to monoidally combine them, we can have this be reliant on a monoid, and we can ensure that the call to mappend in the implementation will dispatch the right instance because we've already done the work of defining those two variants using decal type using that jugglery of Sphene we did before. And so we basically get the same result as in Haskell in our main function. So I know I basically barrage you with a variety of features in C++11, so let's recap. So lambdas, std function, std bind and partial application, auto type deduction, and ad hoc polymorphism with templates. So C++14. So I think I will actually skip ahead a bit more with this. So this is basically offers us a few improvements over C++11. So in this case, we're defining this helper function or this implementation function called mappend, where it takes two arguments of type t, and we have to explicitly say this returns a type t. Whereas in C++14, we can simply say auto so that the type will be deduced for us upon the template instantiation. And then likewise, we can do this additional use of auto in the case of lambdas to form generic lambdas. So in this case of the sum monoid implementation, in 11, I'm using explicit arguments of type sum of t, whereas in the C++14 version, I can simply say they're auto, and it'll be deduced for me. And then finally, in this implementation of mconcat for monoid instances implemented in terms of mempty, I'm calling into a lambda, which is taking two arguments explicitly of type element. Whereas in C++14, I can turn them into auto-ref parameters to turn them into universal forwarding references. So that allows me to perfectly forward the arguments one by one and perfectly preserve not only their type, but also their value category. So recap. So basically, we got basic type inference and polymorphism based on value category. And this is possible to explore with Haskell using things like linear types introduced in GHC9 series. I'm not very familiar with them, and I definitely need to learn more about them, but I'd say it's definitely a possibility. So now for C++17. So the two key ideas underlying this release are essentially basic destructuring and algebraic data types, which we can expand into structured bindings, std optional, and std variant combined a visit. So the case of structured bindings. So if you have a list of subscribers in your business logic, and you have a database of them, say you're a business user and you'd like to generate a report. Normally you'd use a range-based for loop. Now in the case of C++17, rather than having to explicitly use the member access operator in your for loop body, you can do a structured binding to decompose each instance of a subscriber into its component member variables, and then refer to them simply by name without having to use a member access operator to implement your logic. Just a slight quality of life simplification. Then we also do optional. So this is a very interesting data type for composing computations that can have at least or at most one meaningful result. So it's very similar to the maybe type constructor from Haskell. And for us as C++ programmers, what it gives us is an alternative to misappropriating pointers, null values, and exceptions for working with nullable type things. So here I'm defining a struct phone number because oftentimes as programmers we may need to work with phone numbers in our business logic. I'm defining a user which has a phone variable, but rather than saying it's of type phone number, I'm saying it's a std optional phone number to indicate that a user may or may not want to provide their phone number or may be optional based on the business logic. And then since I have this std optional, I can define smart constructors. So given a string view, I can define a validating function that returns a std optional phone number that's only engaged if that string view represented a valid phone number. And then I have another smart constructor for make user, which returns a std optional of user. And so I do a lot of validations to check if all my checks went through. And then if all those parameter checks went through, I return a user, which is transparently wrapped into an instance of a std optional of user. And then otherwise essentially throw or return a std null opt, here represented by an empty initializer list. Then we have std variant and std visit. So this is really a generalization of unions and enums, and it gives you the ability to really define some types from FP languages. And as you'll see, it offers us an alternative to working with rigid inheritance hierarchies. So here's an example inspired by game programming. I know a lot of you may enjoy games in your free time. Some of you may even program games using C++. So here I'm defining two enemy types, slime and goblin. Normally in a game programming context, we might want to implement an inheritance hierarchy where enemy is a supertype of slime and goblin. Here I'm taking a different tack. So here I'm saying enemy is a variant to a std variant of slime and goblin. And so then in my constructors for make slime, I return an instance of enemy. Likewise, for make goblin, I return an instance of std optional of enemy because in this case, I want to validate the input value. Now here comes the magic. So if I want to define freestanding functions which work with any instance of an enemy, regardless of which internal variant is engaged, I can use a special struct template overloaded, which I've helpfully cribbed from cppreference.com. So basically, it inherits from a bunch of type T's, each of which have their own call operator defined. So you can invoke it with different types of input values to dispatch the right function. So if here I'm defining a freestanding function called show, which takes any enemy, and then how it works with any instance of an enemy is by calling the std visit, and then passing as its first argument an instance of our overloaded struct. And then to that, we pass furthermore one lambda handling the printing of slime variables and another one handling the printing of goblins. And then finally, we pass in as our second argument to std visit an instance of our actual enemy. And so what does that gain us? So if we have in our game a bunch of initialized enemies and we'd like to create a database over them, maybe you're doing some ECS, and then you can now iterate over them, and then for each invocation of show, it will dispatch internally to the correct lambda in our overloaded struct, because std visit will take care of doing the work of ensuring it only works with the right variant engaged in that std variant. So how is this useful exactly? Well, it gives us an out for relying on OOP and inheritance. So we can easily define new supertypes and new subtypes by essentially refactoring the list of types that are in the aliases that we've aliased to the instances of std variant. And essentially, whenever we do such refactors, our refactors will be very helpfully guided by the compiler errors we get by the invocations of std visit being incomplete given our definitions of those std variants. So recap, so we got basic destructuring and algebraic data types. So now for 20. So we all know that this is a really big release. So in particular, I'll focus on coroutines, concepts, and ranges. So starting with coroutines. So I actually won't bore you too much with this one. It's actually a very powerful feature. But basically, they facilitate lazy computations that you normally get in a language like Haskell. Very similar to one-shot continuations in OCaml. I feel like they're a bit limited in terms of my ability to replicate things in Haskell, but feel free to talk to me at any time about that afterwards. But I'd highly recommend you talk to or see Dr. Ivan Chukic's talk on Prog C++ from the Meeting C++ conference to understand more about how you can implement concrete functional idioms. So next we're going on to concepts. So I found concepts to be very powerful in terms of being able to represent my intent as a programmer. And for me, trying to emulate functional things in C++, I thought it was very unique for implementing the ad hoc polymorphism that we got with the type classes in Haskell. So this is the C++11 example for monoid simplified. We get rid of all the sphenae jugglery and the dummy type name parameters. And so we can actually define real concepts. So we can say that a type T is arithmetic only if it supports add, divide, subtract, and divide. And then we can say in instantiations of our product type that any such instantiation must satisfy this arithmetic concept. And then finally, for what it means to be a monoid, we can actually say that and express that inside a concept. So we can say any valid of a monoid must have the ability to call mconcat on two instances of that type. And we know this is a valid thing to say because we've already done that jugglery of ensuring that any invocation of mconcat for any monoid will work because we've done the sphenae business. And then furthermore, in our definition of fold map, we can use a concept like monoidal to ensure that any input monoid is truly satisfying the definition of a monoid, where monoidal is a CV qualification handler for monoid. Now for ranges. So ranges are a great tool for doing lazy traversals of data structure, really allow a fluent and functional style of programming that you normally see in languages like F# and OCaml. So once again, to the perhaps tired example of streaming services. So I'm talking about plans like Standard Plus and Ultra. I have a subscriber struct with such plans. And so I start with initial database. I like to filter that down into a target collection of subscribers, and I do that as follows. So I'm essentially creating a range view transformation or pipeline. So I start with subscribers, which itself satisfies range by exporting in a sentinel and iterator. And then now I pipe it into the range adapter stood views filter, which accepts a predicate that I can apply to throw out values that I don't care about. So I first filter on age being less than 36, age being greater than 24, and then I apply another predicate to ensure that my subscriber is not just on the standard plan. And then I project each subscriber into their first name by using the pointer to member. So now I've essentially defined what it means to have a database of target subscribers, and so I can iterate over them using a for loop. And the interesting thing that occurs here is that no computation occurs using this range view pipeline until it is demanded by the iteration of the for loop. So very similar to Haskell. Now you might have thought that was a lot of ceremony, so the question is it easier in Haskell? And since I'm asking the question, obviously the answer is yes. Right? Because in Haskell, everything's defined in terms of functions and function composition. That's the name of the game. So here's exactly the same example as in C++, except I'm working with lists for the sake of simplicity, since I'd have to go into data.vector otherwise. But basically, the one thing you'll notice here is that the order of the transformations is in reverse because of the nature of the dot or composition operator taking the operands in reverse order. But otherwise, everything is the same. Nothing happens in the target subscriber's value in its computation until its elements are demanded by the action of iterating and printing out the list of target subscribers. So recapping, we got coroutines, concepts, ranges. Now for C++23. So here we get stood expected, monadic operations updates to stood optional, and additional helper functions for the range view library. So starting with the first one. So stood expected is very similar to stood optional, except it comes with an additional type error tag for you to essentially give better information to your users or yourself as programmers. So a common domain in which you might encounter failable or nullable or such computations is in working with numerical analysis or numbers. So we know tons of things can go wrong, NaN, underflow, overflow. So here I'm representing that by aliasing arithmetic error to a stood variant of all these such types. And so whereas normally I'd have divide be a function from double to double, double and double to double, and it could silently fail when the double b is 0. Here I'm doing a safe version of double, which in turn instead returns a stood expected of double and arithmetic error. So in the body of my function, I check for these various error conditions, and then if any of them occur, I throw or return an instance of stood unexpected, and otherwise I'd simply return a divided by b, which will be wrapped up transparently into an instance of an engaged stood expected containing my double. So I can define normal transformation functions on doubles as normal, but when I'm working with the failable computation using stood expected, how I thread through a mapping operation like square through the result of a divide is as follows. So when I call divide 3, 0, I have to call the transform method on its stood expected to lift square, a function from double and double to double, to a function, or sorry, double to double into a function from stood expected of double to stood expected of double. And so based on whether the result of divide is engaged or not, square will then kick in. And then I contextually convert that whole result into a Boolean. And if it's engaged, I'll simply print out the internal value, and then otherwise I'll print out some error message. So as far as pseudo-optional, the monadic operations updates are very similar. If you understand pseudo-expected, you can basically transfer over your knowledge to pseudo-optional, especially considering it's a simpler interface. And then additional range view library support. So here I'm taking inspiration from social media. I'm defining a basic user type. I'm defining a social network, a graph of users. Here are a bunch of users of historical people I just happen to know, in particular Ada Lovelace, Abraham Lincoln. And I'm adding them to my social network. I'm defining bidirectional connections between them because unidirectional friendships would be very lonely, we all know. And then, so as a operator or say a data scientist in the social media company, maybe I'd like to find out all the second degree connections of a particular user. So here in this case, user one or Ada. So I start off by defining first, which essentially is the result of doing get neighbors on U1. And I'm doing some filtering to make sure I don't get Ada again in that list. And then I define seconds by starting with first, which itself is a range, and then piping it into std_views transform to get each of the neighbors of the users from the original name. So I'm transforming this range of users into a range of users. And then I avail CPlusPlus23 to use std_views join to flatten that range of users into a single range of users, my second degree connections. And once again, I'm doing an incomplete and incorrect implementation of filtering to remove one duplicate, that is. And then, as we've seen before with ranges, I can iterate over them. All the computations are lazy, so nothing is demanded until the for loop demands it. I can actually refactor this example as a generator. It's much more imperative in nature in the internal implementation. So we use a double nested for loop. The outer one iterates over the first degree connections. The next one iterates over the first degree connections of the first degree connections. And then we can actually co-yield each such connection because the generator is actually an instance of a coroutine type. And so in my main function, I can actually iterate over the result of second degree connections as before. And this will occur lazily just as it would with any other range. And we get the benefit of laziness there. So to recap, we get pseudo-expected, pseudo-optional, and its monadic operations updates, and range view updates. So looking to CPlusPlus26 and beyond. So the things I'm looking forward to most based on my research are essentially more pattern matching and destructuring, do expressions, and additional helpers of the range view library. So as far as pattern matching and destructuring, this has been described by various papers. I can't admit to having read all of them. I know that there's the famous is-as paper by Herb Sutter. So basically any instantiation of this idea in a future C++ would basically allow us to work on the shape of data as algebraic data types to really avail of their full potential. And since this is a systems programming language, it should allow us to engage in fine-grained control of resource and ownership transfer as well as referencing of destructured values. So do expressions. This is described by P2806, and I believe it is by Timur Domler. Please forgive me if I'm pronouncing your name wrong. But this is very interesting in terms of allowing us to eliminate the need for immediately invoked lambda expressions in the language. But that's just one benefit. But the more concrete benefit, I feel, is that it would turn C++ into a more value-oriented language in the style of Rust or Haskell. And then finally, another thing I expect to see is ranges improvements. So a few papers describing this. One thing I would like to see in the language is the ability to fold over nullable types that contain 0 or at most 1 value and be able to iterate over them just as I would be able to iterate over a maybe type in Haskell. So overall, I see a very bright future for C++. If you aren't already impressed by the barrage of functional features that C++ has to offer, I think it's going to get even better in the future. However, I've left a big elephant in the room. And of course, being C++ programmers, you know that elephant is performance. So the question is, will using FP make my code go faster? Will it go brr? Right? For me, there is no clear yes, no answer. The only answer, if there is any, is to use profiling. So there are quite a few inlining resources that I looked at to understand this topic. And you could partially argue that this is a bit of a cop-out, but there are very smart people, much smarter than me, who have discussed this issue in great detail. In particular, Dr. Strausrup, Dr. Carl Cook, Schacher Schmesch, Klaus Igelboge. So they have various opinions and results pointing to the idea that there may be no clear answer as to whether FP or imperative or OOP will be faster in any case, generally. So if I'm saying that, why did I come here? So there's a few reasons. And one is that source code, I feel is isomorphic, or maybe not isomorphic, but equivalent to human language when it comes to the work of programming. We all know that famous Harold Abel Sen quote, which I believe comes from SICP, in which he roughly says, computer programs are meant primarily for humans to read and only incidentally for machines to execute. So there's this important idea that source code should be made for people to understand, for you to understand, for your juniors to understand, for your coworkers to understand. And I also believe that imperative code doesn't really lead to strong denotation. So denotation is basically a concise and clear mathematical meaning. Imperative code can be specified very expressly in terms of operational semantics, but for us as humble programmers, we can't have some kind of virtual machine or interpreter running in our heads all the time to be able to understand the legacy code we wrote 10 years ago. And that really leads to the notion of denotative code leading to compositionality. So I'm cribbing somewhat the ideas of the great Dr. Connell Elliott of Haskell and Agda fame, in which he says that we should be able to understand the meaning of a composition of subprograms by the composition of the meanings of the subprograms. So I'd like to think of this as being a sort of locality of behavior, which I believe is referenced by the HTMX creator in his blog post. This idea that we shouldn't have to refer to a whole context of our entire production code in order to locally reason about our code, and so we can get going faster in refactoring, coding, and so forth. And I also believe that denotative code can lead to better optimization, even though I probably said to the counter right before, right? So here's what I'm talking about. So I'm here giving a very caricatured example of imperative code where I've inlined the imperative action of printing out some list of target subscribers and then juxtaposing it with the actual logic of filtering out subscribers I don't need. I'm using continues, which are just glorified go-tos. I know you may not write code like this, but this just goes to show the idea that what may occur when we try to optimize for maximal performance. But the other important thing is that this is not very composable, right? So if we were to take this filtering code reliant on continues or go-tos, we can use it here, but we can't use it anywhere else. We can't transplant that and put that somewhere else and expect it to have the same meaning. Whereas if we use range views and we separate out our imperative IO actions from the actual act of declaring what it means to have a collection of target subscribers, now the compiler can say, I know what you're talking about. You're defining a range view. I know exactly what the denotation, what the meaning of that is. And it can do the work of inlining things for me. And maybe if I reuse that somewhere else, it can do the work of optimizing into the ugly imperative code I normally would. Now, this might not be true with current GCC or Clang. I'm not a compiler expert, but I expect this to be truer in the future as compilers get smarter about recognizing high-level algorithms and structures that we use in modern C++. So overall, what I'll say is that the future for us as programmers is functional, or rather denotational. So that's basically the end of my talk. So this is basically all a ploy for me to get a job. So I'm looking for my next adventure. So if you're at all interested in Haskell or C++, or you want a programmer who's interested in creating robust, performant, and maintainable code, I'd love to have a conversation with you. And basically, I'd like to thank you so much for coming. And I'll end off with my bibliography. Thank you so much once again.